You are looking at the zero gradient synchrotron at Argonne National Laboratory. It is one of several kinds of particle accelerators, the basic tools of high energy physics. This unit is made up of dozens of giant electromagnets, each weighing many tons, arranged in a circle 200 feet in diameter. Impressive. Yet there are other accelerators being built even larger. Physicists need such machines to explore the atomic nucleus. What is the atomic nucleus? Physicists can't give us a precise answer because their concepts of atomic structure are continually being modified. An atom of hydrogen, the simplest element, was once thought of as a negatively charged electron cloud distributed about a nucleus made up of a single proton, a positively charged spinning particle having much greater mass than an electron. But in a high-energy reaction, the proton sometimes acts as if it were a combination of a spinning neutral particle called a neutron and a pi meson. At other times, the nucleus acts like a combination of yet different particles recently discovered, a K meson and a hyperon. On still other occasions, it seems to be made up of yet other combinations of particles. Physicists do not know how many particles may be present, nor do they have accurate laws describing the forces acting between them. The only way to learn about nuclear particles is to bombard them with other particles and to observe the reactions. To do this, the particles are raised to high velocities. This is generally done in a series of stages, beginning with a Cockcroft-Walton generator or similar machine, which starts particles moving at relatively low velocities. Particles can be raised to higher velocities in a linear accelerator, which is made up of a series of hollow electrodes arranged in a straight line. From a linear accelerator, particles can be shot into a circular accelerator, such as the synchrotron we saw earlier. Circular accelerators usually provide the highest velocities and energies. Through the curved metal channels on the floor, particles are shot around and around the accelerator, receiving an electrical kick each time they pass through. After whizzing around about 1,000,000 times in a single second, the particles reach 99.75% the speed of light, with an energy of 12.5 billion electron volts. Once the particles reach this velocity, a target inside the machine is swung into the path of the particle beam. Collisions between the particles and the target nuclei produce the interactions and new particles which physicists wish to study. When bombarding particles approach a target nucleus at some distance from its center, they don't react with great energy. As particles come closer, greater amounts of energy are concentrated in the target region, and the likelihood increases that other particles will be torn loose from the nucleus or created as a result of energy being transformed into mass. Once these particles have been created, they are directed through large metal tubes to various detection devices, which physicists use to learn about how the particles behave. One of the simplest of these devices is the Cherenkov counter. Particles entering the counter pass through a gas-filled cylinder. If the particles are going faster than a certain velocity, they create a flash of light in the gas, which is reflected to a light-sensitive photomultiplier tube. The photomultiplier converts the light into electrical energy and amplifies the signal, which is then sent through wires to an electronic counter. Another commonly used detection device is the scintillation counter. In use, it is wrapped in tape, which we can remove to reveal the working element, a piece of fluorescent plastic. When a charged particle smashes through molecules in the plastic, some of its energy is converted to a pulse of light. The light is sensed by a photomultiplier, as with the Cherenkov counter, and converted to an electrical pulse. A single scintillator can be used to detect when a particle passes through a given area. Two scintillators together can be used to detect the paths of particles. 2 points, remember, determine a straight line. Particles entering from outside the beam line will excite one scintillator or the other, but not both. Both counters will detect only particles along the main particle beam. Counters set up in this manner can be used to turn on other detection devices placed between the two counters, as this spark chamber. Particles activating both scintillators must pass through the chamber. Each time a charged particle passes through the chamber, electrodes inside are raised to a high voltage. This causes sparks to jump between the electrodes along trails left behind by the particles. This gives visual indication of the paths the particles follow. Each spark represents the path left behind by a charged particle. Sometimes, particles from an accelerator are directed along a beam line into a mammoth detection device containing both target nuclei and means of recording the paths of interacting particles. This is a bubble chamber. The chamber contains liquid hydrogen under pressure. At this end of the chamber are round windows through which light is directed. The light will silhouette particle interactions which take place within the hydrogen. At the opposite side of the chamber, cameras are installed which photograph paths left by accelerated particles colliding with hydrogen nuclei. Pictures are taken every few seconds, recording thousands of interactions daily. A photo of the inside of a bubble chamber shows trails of tiny bubbles. Each bubble trail indicates the path followed by a charged particle as it passes through the chamber, much as each spark on this photo of a spark chamber shows the path of a particle passing through the spark chamber. Using a bubble chamber photo, we'll demonstrate some of the techniques used by physicists to learn about particle interactions. The scientist begins with the information that the tracks on this particular photo resulted from incoming protons from an accelerator aimed at a hydrogen target in a bubble chamber. The tracks which continue all the way across the photo represent protons that went through the hydrogen target without hitting anything. But this one indicates a proton that collided with a nucleus to produce other particles, pi mesons, k mesons, hyperons, and others. The physicist learns about the nature of these particles through a series of inferences. He knows that all of the tracks were produced by charged particles. Uncharged particles do not leave tracks in a bubble chamber. Perhaps the gaps between tracks, then, represent the paths of uncharged particles. These provide links between the initial collision and the subsequent appearance of other charged particles. The short length of these lines indicates that the neutral particles lived for just a short time, on the order of a 10/1000th of a second. Then they decayed into the charged particles. Further inferences on the behavior of the particles that passed through the bubble chamber are based on the knowledge that the chamber is surrounded by electromagnets, producing a strong magnetic field. A magnetic field exerts a force on charged particles, causing their paths to curve. Some of the particles curve toward the bottom, in the same direction as the incoming proton. The proton has a positive charge. So the researcher infers that the other particles curving in this direction also have positive charges. In contrast, the remaining charged particles curve in the opposite direction and must carry negative charges. Further inferences are based on the amount of curvature. Particles curving the most are most influenced by the magnetic field and must have the least momentum. Conversely, particles curving the least are influenced least by the magnetic field and must have the most momentum. We've seen some of the gross techniques used on first inspection of bubble chamber and spark chamber photographs. More sophisticated scanning devices are used to examine these photographs rapidly. A great number of collisions must be checked to arrive at generalized laws regarding particle interactions, many of which are statistical in nature. A researcher may want to know how many times in 1,000 or 100,000 a certain particle event will occur. To find relationships among the great number of events they are trying to describe, researchers also feed data from particle interactions into electronic computers. It's a costly, time-consuming process which seems to have no foreseeable end. Physicists are continually having to modify their theories and laws to account for new information gained as they probe deeper and deeper into the mysteries of the atomic nucleus.